Hi there, it's time for another video on my Heathkit H8 computer. If you've watched previous videos, you've seen me take the stock CPU board that this computer came with, which was based on the Intel 8080, and replace it with a variety of CPU boards. Now that includes going to slightly more capable CPUs like the 8085, which can run a little better clock speed, as well as going in the other direction to something like the 8008, the first 8-bit microprocessor, running at a much lower clock speed with a more constrained feature set. In this video, I'm going to go well in the other direction and go to the 8186 CPU, running at 25 megahertz, addressing a megabyte of address space, and capable of running MS-DOS, which you can see up here on the serial terminal. So this is really going to be a video not just about the H8 computer, but about the x86, and particularly the 8186 CPU. Now, if you were involved with computers in the 90s and the 80s, I'm sure you'd heard of the 8386, the 8286, the 8086, and of course the 8088, with the 8088 being very popular in the IBM PC, which a lot of people either own PCs or PC clones. Not many people have heard of the 8186. There were a few computers that used it, in particular the Tandy 2000. Did you own a Tandy 2000? If so, please respond in the comments and let me know about it. I did not own a Tandy 2000, and I don't know anybody that did. I did own a Tandy 1000, but that went back to being based on the 8088. The 8186 was also used in some other computers like Convergent Engine, which I have done some videos on. And the 8186, what makes it different is it has a set of onboard peripherals. Now those include a variety of things that you would have had to add to a traditional x86 CPU to make an IBM type computer. Things like the interrupt controller, the DMA controller, the programmable timer generator, I/O addressing logic. All of those things are built into the 8186. However, they're built in a way that is not identical to the IBM PC. In a lot of ways, it's done better, using a better mechanism for I/O addressing. But because it's different, it's not fully hardware compatible with the PC. And some early PC software would assume the existence of that timer chip at its specific port address, or the interrupt controller at its port address, etc. They would make assumptions on that. You might have even programmed the DMA controller directly if you wanted to do high performance memory transfers. All of that will not work typically on an 8186 based computer because the addresses and the configurations of those chips are different. So that led to a little bit of compatibility with PC software. Software that used the standard BIOS int 10 would work fine because you could write a BIOS to use those chips. Software that used the standard DOS interrupt 21H system calls would also work fine. But a lot of people would bypass that and go directly to hardware. And one of the places they would specifically do that with the video adapters. So back with the PC, the original PC, you would have had either an MDA monochrome adapter or a CGA color adapter. Or you could have upgraded to something like a Hercules or an EGA or VGA for better graphics capability. All of those use sort of a video RAM frame buffer type approach where a program could directly write to the video RAM and have characters appear on screen. I do not in this computer have a CGA or an EGA or an MDA or any kind of video adapter like that. This is going to use a straight serial port. You are seeing video output up here. But that's because I have a parallax propeller based dumb terminal hooked up to it, and that dumb terminal takes a serial, displays on the VGA screen. It's the same dumb terminal that I used with the 8008 board and the 8080 board, the 8085 and other boards with this computer. That is an awesome video terminal. It's called, I think it's called the Microsoft Propeller VGA terminal, something like that. I'll put a link up. But I use that in a lot of my projects. So that's how we're getting video output from the serial. So because we have no native video adapter in this, the software cannot write the video memory locations directly, and that will be another source of incompatibility. Now the other thing that's a little bit unique about this on the H8 is that this 8186 is a true 16-bit, both internal and external on the data bus CPU. There is an equivalent to it, the 8188, that is 16-bit internal with an 8-bit external data bus. But just for fun, I wanted to do 16-bit and do 16-bit memory addressing so that we can get additional bandwidth out of our RAM. So how do you do that with an 8-bit Heathkit computer? Well, I put all of the RAM on the CPU board as well as the ROMs on the CPU board, and then I use the Heathkit's bus as strictly as an 8-bit I/O bus. So I intentionally started this project out not with the intent of making just a single board computer, although it does function as that, but making a single board computer that could use these H8 peripherals, including the front panel display, which you see is currently running its front panel monitor. Now I'm going to start the design phase by talking about the SBC-188. The SBC-188 is a project that you can find on the RetroBrew computer forum. And I built one of these myself a couple years ago and did a video on it. So if you want, you can go back and dig that video up and see one of these in action. But what it is a board that uses the 8188 CPU, which is the variant of the 8186 that uses the 8-bit external data bus. You can see it's got a variety of capabilities here, including the megabyte of addressable space, an 8255, IDE, onboard floppy, onboard UART, etc. Looking at the board down here, you can see it's an amazingly compact board. There's the 180 is there. It's got a couple of RAM chips to do the megabyte of RAM. It's got a ROM chip here for the memory, and then over here would be the floppy and the UART. And then they have a bus here that goes to the bus that the people over on the RetroBrew forum use. So this was a great starting place for me, but I wanted to do a 16-bit board. So I started with their basic design and their BIOS, which is really important because BIOS is a hard or a time-consuming thing to write. But I started with their design and their BIOS, and then I morphed it for 16-bit. So let's transition now and look at my. Okay, here are the schematics for the H8 8186 board. Now there's about 6 pages to this, so I'm not going to go into it in a lot of detail. It is very similar to the SBC 188 from RetroBrew, as I mentioned before, with the obvious changes necessary for it to be a 16-bit data bus rather than 8. So our 8186 CPU is sitting here in the middle, and it's got a clock oscillator currently at 16 megahertz. It divides that in half, so this would be for an 8 megahertz CPU. For the 25 megahertz CPU I have out there, I'm using a 50 megahertz oscillator. The reset is handled by an MCP 130, which will automatically reset based on the voltage. Now the address and data bus are multiplexed together, so AD0 through AD15 are both the address and the data bus. So what we will have is a couple of latches here that when this ALE signal is present, that's address load enable. When that signal is present, we will latch these the shared bits here, and that will give us the first 16 bits of our address. We'll also at the same time latch the upper 4 bits. That gets us to a 20-bit address, as well as the state bits S0 through S2 and BHE. BHE is your bus high enable. Now, this being a 16-bit CPU, it can address 2 byte. You can transfer 2 bytes at a time. So a byte on the D0 through D7 and a byte on the D8 through D15. BHE, when it is active, will tell you that the upper line, so D8 through D15, are valid, and it wants to transfer that half of the word. Now, there is no BLE, but what it actually does for bus low enable, what it actually does is BLE is shared with A0. So when A0 is set, it is asking for the low byte or data lines D0 through D7. So that gets us our 16-bit data bus and our 20-bit address bus, our state bits, and our high and low enables. Now, when we talk to I/O devices, we want to talk to those 8 bits at a time. because most of our I/O devices are 8 bits. So that's what these bus transceivers here are for. Now, one option is you could simply use only even addresses. If you use only even addresses, then only D0 through D7 are used. You'll never use the odd ones that are up here, D8 through D15. But that is really inconvenient because a lot of software is designed to use consecutive addresses in a device and is not designed to use only the even addresses. So what I did is I stuck 2 transceivers on here, and assuming that we only do an 8-bit I/O port address, when the low byte is asked for, we will take D0 through D7, and we will put this on this ID0 through D7. And that is what I'm calling the I/O data bus. And on the other hand, when the high is enabled, we'll take the upper byte and we'll put it on those lines. And these are bidirectional, so it can go either way. So that's how we take the 16-bit data bus, turn it into an 8-bit I/O bus. Now there's a couple PLD sections that have the logic that drives all of this bus and addressing. So first we have this one here called the bus PLD, and it looks at the CPU state bits, some memory selects, the bus high enable and the bus low enable. Recall that's the same as A0. The data transfer enable, and the ALE. And it will generate the RAM and ROM chip selects, an M1 signal, and these D high and D low that run these two addressing selects here for multiplexing the 16-bit data bus down to 8 bits. It handles all that. The other one here called I/O handles most of our I/O selection logic. So it's got PCS 4, 5, 6, as well as 0 and 1. Those handle various I/O selects out of the CPU. You've got A4, 5, and 6, which are some addressing bits, memory write, memory read. And out of it, we will get the chip selects for the IDE device. The H8 bus is read and write. The floppy, the parallel. It's actually, we don't have the parallel port, but I still left it marked as parallel port. The UART and the IDE and the latch for the diagnostic LEDs. Now down here, we have some stuff for mapping interrupts. Page 2 is the H8 bus. So this is the H8 connector over here. There's only one pair of these in reality, but there's 3 different footprints, so you see 3 sets of them. We've also got a connector here for the front panel. There's a 74 HCT 640. So all of the lines on the H8 bus are inverted logic. That's kind of unique to the H8. So what we need to do is we need to take those ID0 through ID7, that's our I/O data bus, and invert it when putting it on the H8 bus. So that's what this buffer here does. Similarly, we need to do that with the address lines A0 through A7, invert them. Page 4 is the memory devices. So you've got a megabyte of ROM and a megabyte of RAM. Being a 16-bit computer, and that we're actually using the 16-bit data bus for the memory accesses, these do hook up to both the lower and upper data bus lines. Page 5 is the UART, and this is a 16C450 or 16C550 UART. It's got its own 1.8432 megahertz clock and its MAX 202 driver, and it just comes out to some headers. Not a whole lot to see here on the UART page. Now, the UART is technically optional because what I do and what you'll see in the demo is that I have disabled the onboard UART, and I am using the UART on my serial board that's in the computer, my H84 serial board. So again, one of the things I wanted to embrace with this was to use as many of the H8 peripherals as I could. There is down here a Dallas 1302 clock. Now I got this from the SBC 188 design, and it's hooked up in a really unorthodox, kind of weird manner here, which I think was for them to reduce chip count. So rather than hooking this up to data lines directly, as they did in one of their earlier revisions of the SBC 188, they used some of the lines on that UART. So they used the carrier detect, the DTR, and 2 of the general purpose outputs. And again, that's just them saving a couple of chips because they crammed a lot into that SBC 188 board.
Okay, and here we have the floppy controller, the WD37C65. It's 34-pin connector and some pull-ups. The signals going to the floppy drive need pull-ups. It's also got its associated 16 megahertz oscillator. Now, I ran out of room in the PLD, so in the SBC 188, they were able to fit all of their I/O decoding and other decoding in those two PLDs. But when I went to the 16-bit bus and the extra complexity of the high and low data bytes and all that, I didn't have enough room. So I added a third PLD, which generates these floppy signals. So it takes a floppy chip select as well as 3 address lines, and it will turn on the terminal count, the CS, the DMA ACK, the operations register load, and the control register load. You'll also see some stuff down here about interrupts. That's part of the next revision of the board that I'm working on. Just needed some space to implement a little extra logic down there, so I'm using part of this PLD. Not going to explain this interrupt stuff because I don't actually have that part working yet. And then down here we have the compact flash. Compact flash is super simple to interface to an 8-bit retro computer. I used a buffer here. It takes those ID0 through ID7. That's those I/O data bits, as well as a direction and a chip select, and it buffers them onto D0 through D7 on the I/O connector for the compact flash. Technically, you don't even need this data buffer. I've seen many implementations where they won't buffer it, but I think some compact flash devices are less stable when you stick them directly on a bus, so this helps. The upper 8 bits, I just pulled those high with a resistor network. We'll use the compact flash in 8-bit mode. It's simpler to do it that way. And then you just take that pin out from the compact flash card, and then you also wire it over here to a 40-pin IDE header. That allows you to use a disk on module or an external 8-bit IDE drive. It would have to be an 8-bit one, not a 16-bit one.
Here is the H8 8186 CPU board. So right here in the middle, the square chip is the 8186 CPU. It's actually an ADC 186 XL-25, which should support a 25 megahertz frequency. Over here, we have the various address buffers and data buffers for the address lines and for the data lines. Remember, this is a multiplexed CPU, so the buffers or the 16 AD lines are shared between address and data. And then we have our data buffers so that we can route those selectively to the 8-bit bus. There's also one down here for the control lines. We have 3 programmable logic devices that handle our bus logic, some I/O addressing, and then some additional I/O addressing for the floppy adapter. Our memory devices are over here. So a total of 2 ROMs. These are 39SF010 ROMs. They're actually flash chips. They're just what I had in my junk box. Next to the 2 ROM chips are the 2 RAM chips. Now those are AS6C 4008. Those are each 512K. Together they'd give us a megabyte. Over here we have the H8 bus connector and the bus transceivers for the H8. Over here for peripheral devices we have our 16550 UART and our WD37C65 floppy controller and their associated crystals, crystal oscillators, a 1.8432 megahertz and a 16. Down here we have our real-time clock, Dallas 1302, with its associated 32.768 kilohertz. Spot for memory backup using a super cap, not currently populated. Max 202 driver for the serial port, coming up here connecting with your serial header. Header here would be for the floppy, standard 34 pin. We've got our compact flash device here and an 8-bit I/O buffer for it. We operate the compact flash in 8-bit mode, and those lines are also plumbed out here to this socket in case you want to plug in a 40-pin DOM module. Okay, let's go ahead and install this in my H8. So in the H8 we've got a few boards already. This back here is my dumb terminal board and VDIP USB board. And it actually has a propeller serial terminal, the Microsoft serial terminal. It's got a VGA output and a keyboard input, and this just implements a serial terminal. So it's got a 16550 UART on it. We'll use this UART rather than the UART that is on the 8186 board. It's also got Raspberry Pi. It's kind of hidden back there that I can use to transfer files back and forth to the vintage computers. I usually keep this in the H8 because it gives me a serial terminal and the file transfer capability. Then here I have my speech synthesizer. I'm just going to put that in there so that we can play with speech synthesizer a bit. Go ahead and we'll put the board in. You have to hook up this little pigtail for the front panel. Then we'll put the board in right up here near the front. And that should be good to go. Okay, so we've got my monitor hooked up to my propeller serial terminal. Also down here I've got a keyboard. Let me go ahead and turn the computer on. So the bootloader starts running immediately. It starts counting down its post check here, and it finds that the NVRAM in the DS1302 clock is invalid. That's because it hasn't been set yet and it has no battery backup. A little bit of gibberish here because we actually booted up the propeller serial terminal at exactly the same time that the computer was booting, so it didn't get the initial spew out of the copyright notice and such. But anyway, right now is a very good time to look at the monitor here. So this is your standard Heathkit style front panel monitor. I had to implement this from scratch because obviously the one for the 8080 it doesn't work on the 8186. The radix is currently in octal, as is typical of Heathkit. I can switch it over there to hexadecimal. And we're looking at an area in memory. This is offset 00D0. That is the value there. Since this is an x86, we've also got a segment register, segment 40. This is actually part of the BIOS data area down at segment 40 and 40 hex. And what this has is a lot of BIOS data in it. I stuck some of my own stuff in there and some of the unused locations. And this here is a simple cycle counter of the front panel refreshes that get updated about every 5 milliseconds. So let's go look for something else interesting in here. It takes me a little while to page back here. See, lots of stuff goes by. And get down to about 6. Oh, there's 1, 2, 3, 4. That's like the warm boot signal. 6C, and we run into another counter. This one is actually part of the standard BIOS, and this is the 18.2 times a second counter, which I think all PC compatibles have that. It's your standard counter sitting down there. Now we can also modify memory, so let me just switch it back to octal since I'm more used to that. I'll go out to some random high address. Let's go 200374. There's currently a 000 there. I could alter that. I could change it to a 1, 2, 3. Goes to the next address automatically. There's another 0 here. 341. And we can see it took my values. So you can use this to examine memory, alter memory. You can look at the registers. So again, this is the segment that it's displaying here, but I've also got CS, IP, AX, BX, CX, DX. I haven't fully populated out the monitor. Next thing we're going to do is to configure this NVRAM, and we'll just set the date and time, 12/20/23, and it is currently 11:25. Actually, it's PM. 23:25. We'll do one ID disk. I didn't select any floppies because I don't have any floppies plugged in. Then I'm going to change this to 115200. And it actually continued at 9600. It doesn't take the baud rate change until we reboot. So what I'm going to do, I'll update the terminal to 115200. There we go. And we'll go ahead and we'll reboot the computer. And now it is at 115200 baud. You saw the copyrights go up. So we've got Sergey's Video BIOS. We've got Retro Brews, SBC 188 BIOS, some of my modifications. And here we are down here in MS-DOS. Continue. And we're in familiar DOS environment. Now some things, I want to disclose some things in this don't work right, so let's try to run check it. And I think what happens, boom, it just dies. It doesn't do anything. I think what happens is maybe some of these things they're expecting a true IBM compatible, And this is not a true IBM compatible. This is an 8186. It's got different registers for the DMA, different registers for the interrupt controller. It has no CGA adapter, so some software just won't work on it. Check it as one example. Another example would be GW Basic. Now GW Basic will almost work. You know, look, it loaded the screen right here, but you know, it's not actually taking any. It's not actually doing anything. You can't actually exit it, so not great. After running GW Basic, it kind of glitches the terminal, so I have to reset the terminal. That wasn't resetting the computer, that's just the Parallax serial terminal. And we're back in DOS again. Now, even though you can't run BASIC interactively, you can run some BASIC programs on it. So if I go into Games, Friendlyware, and let's do DOS GW Basic. I'm going to run hangman.001. This is actually a BASIC program. The 001 extension should be .bas, but Friendlyware, they named it based on the disk that goes in. No instructions. Oh, that ought to be an easy one. A O U E I Y. Maybe it's like try. Whoops. Here, let's just try another letter. I think it is. No, it wasn't try. Could be cry. Fry? There we go. We got it. But the game actually locks up here. So I think what's happening is, I know this game will play some music, and this does not have the IBM compatible speaker in it. So maybe something is wrong with the music. Anyway, that's just a guess. I'm going to reset the terminal. Come on, terminal, come back, and then reset the computer. Some programs do run just fine, so let me do Zork 1. This is actually Infocom standard Zork. Take leaflet, go let's southeast, open window, enter window, west, move rug, open trap door, down, north. There, that is the quickest I've ever died in Zork. Got it in, like less than a minute. Quit. So, let's go back to the root here. What else can we do? Oh, Galactic Warzone. I know this game well. There in the serial terminal, it's somehow it's missed an escape sequence and a little glitch down there in the status line. Play the game. Let's go out to sector 2000. I'm in that sector. Oh, I've been playing before. Let's go back to sector 1. Sure. Galactic Warzone. Works just fine. I think anything that just uses plain ordinary text mode DOS will probably work fine. What else do we got here? I've got some things, let's see. This is actually plugged in. I have some additional boards plugged into this, so my speech synthesizer board is in here. Speech synthesizer. Oh, here, let me. Again, we've got a little issue with some windowing on the terminal, so reset the propeller VGA terminal. Okay, so let's run. The say command is a text-to-speech program, so we'll do this. Is a test.
This is a test.
All right. This is an H. Sometimes with the text-to-speech, you have to kind of lead it to say what you want. If I just put an H, won't get it. But if I say like H, maybe H8 computer AT. Oops, 186 CPU.
This is an H8.
Okay, so that's my little text-to-speech program. Got some other stuff sitting in here. So another board I have in here is this Vinculum VDIP1. Is a USB adapter that I use with many retro computers. Has some software in here that was written by Glenn Roberts for the H8, and I ported it. So you can actually get a directory of what's on the USB. Okay, good. It worked. So you can see what files are there, and I could do like a vgit bruteprime.com in there. My prime number, world's worth prime number generator. There we go. But the Vinculum utilities make a really easy file transfer mechanism. Sure, we could use something like Xmodem, run a serial terminal, but this will actually use the VDIP with the USB, or with a Raspberry Pi emulator for the VDIP that I developed. So you can actually put files on a Raspberry Pi, transfer them on here. It makes for a great developer experience. Not much else here. I do have FP off. Turns off the front panel. FP on. Turns on the front panel. I ported LB Forth, which is a Jones Forth equivalent. It still says Olivetti M20 because that's the last time I was using this. You know, .s. Your typical Forth. Whoops, I did that wrong. Let's try that again. Words. Typical Forth. Forth is great language, fun to program in. In conclusion, I hope you enjoyed this video on the H8 186 CPU board. I certainly enjoyed building this CPU board for this H8 computer. It was an interesting experience, particularly to understand what DOS software I could and could not get to work with it. And I was happy that I was able to get several DOS programs to work on it. Anyhow, please subscribe, and please come back for other retro computing videos. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and Sandrail stuff. Bye.